to the club. So, good morning, everyone. We're going to spend 2 hours on both compressed air and liquefied air energy storage. There's a lot of mechanical engineering related theory, concept, and equations here, but they are very useful even for other courses when you talk about like turbine, compressor, power generation. All the equations you see today will be very useful. And then, if time allows, we'll also go into the Exergy aspects a little bit over here, also from a general perspective. So let's start. So here we're going to look at some examples of compressed air energy storage systems. We will identify and distinguish the difference between closed and open system. For those who have taken the RET course with me last year, this will be just a recap, a summary. And then maybe I will not derive it on the screen, but I will show you how we get all these equations. I have a few backup slides here. And then we will go to some system studies of liquid air energy storage, as well as a few words on Exergy aspects. Over here is shown a picture of a compressed air energy storage system. Maybe we can have someone to sort of explain it in a few words. Any ideas how this works? You have seen this a few times, right, throughout different courses. Any suggestions on the principle? Comments? So basically, it's very straightforward. When we have excess mechanical work or, let's say, electricity, we can operate our compressor, which would compress the air. We store the compressed air. It can be diabatic, meaning that we lose the heat. It can be adiabatic, meaning that we use a thermal energy storage, or it can be that we just insulate the whole system very well, so without thermal energy storage, but our air is heated up. It can be isothermal. That means we compress at a very slow rate, or we remove the heat during the compression. And it can also be supercritical compressed air energy storage. When we want to take out the energy, then we heat up the air if it is in the diabatic system. If it is adiabatic, that means the heat that is stored, it will be taken away by the compressed air upon expansion, right? So then here we run, so in this case, with a combustion chamber, this is the case when we have a diabatic system. And then we run our turbine. So we have a high pressure stage and a low pressure stage where we recreate mechanical work, or we convert the compressed work to mechanical rotation, so kinetic energy that we can use to produce electricity by running a generator. The concept was started already in the 40s, and then in the 70s and 80s, we had the first large compressed air energy storage systems, and now there are a few more. So here the latest one was in Jiangsu in China, Jingtan Salt Cave, where they had 60 megawatts of power and 300 megawatt hours, so 6 hours of storage capacity over there. This is another picture of compressed air energy storage concept, where we have, in most of the cases for large systems, a salt cavern. This is where we can ensure that we don't have so much leakage. And then upon expansion over here, we can have different stages. And also in the compression stage, when we compress the air, we can have several different stages so that we can run our intercoolers to cool down the air in compression. So here we see a picture from Joe Stock over here. A few examples of larger size compressed air storage systems. One is in Germany, Hontor. efficiency is 42%. This is a diabatic system, meaning that they lose heat. So they have to provide heat back from a combustion chamber. It is 650 meters deep. It was commissioned since the 70s. Here you see that the operation pressure ranges from 72 to 46. So this is similar to pumped hydro. When you discharge, the level goes down, right? So here, when you discharge, the pressure goes down. And this system operates from the maximum pressure, 72, when it's fully charged, down to 46. Similar to your battery, like you can have a level in your battery and you stop it when it reaches a certain minimum voltage level. And here is a minimum pressure. So you have two stages of turbine. High pressure, 42 bar, is always running at 42 bar, and the lower pressure stage at 11 bar. So here, basically, you have an expansion valve here, where you expand it so that it is suitable to be run inside your turbine. You'll not design a turbine that is at the max pressure, because after the slight discharge, when you start discharging it, it will drop in pressure for sure. So that's why you design it a bit lower than your operating pressure range. And then for charging, then you have the compressor over here. So this is for charging up, and then with potential intercoolers. Some characteristics of this Huntor compressed air energy storage system, comparing with that in the States, in Alabama. This was built a few years later. Here you see that the power, so in the States, it's 60 hertz. In Europe, it's 50 hertz. So you see the differences in the frequency of the electricity generated afterwards. Air storage, you see it's 4 hours. So the power, 290 megawatt times 4 hours, you get the storage capacity. Here in the States, 110 megawatts for 24 hours of storage capacity. So you multiply them and you get the total storage capacity. The sizes are compared here, and then also the flow rates. So those are some just specifications. Here are some more operating conditions for the Huntor, the German plant. You see data on the compressor, data on the cavern, data on the turbine over here. So if you're interested, you can dig deeper into it. And you see the flow rate is extremely large, 400 kilogram per second. And then, yes, the operating pressure, 46 to 72. The picture to the right is shown the CAES, compressed air energy storage, in Jingtan in Suzhou, China. So 5 hours of storage capacity at 60 megawatts. This is an analysis on the Huntor plant. Here you see the pressure on the y-axis, time on the x-axis, and then bottom left, temperature on the y-axis, time on the x-axis. You see in blue, the isothermal model. So this is the pressure if we're working in isothermal state, so no temperature change. And then you have the case with the adiabatic model. It's also a simulation in black dashed line. Then the experimental case is shown in the dots here, so green dots. And then the actual model, or so they retrofitted the model so that it fits the experimental results, is shown in red. So we see that the two extremes are the isothermal model and the adiabatic ones. So adiabatic means no heat loss. Isothermal means that we have constant temperature. To the bottom left is shown the temperature change over here also. So isothermal, constant temperature. But then in reality, it is closer to the adiabatic model over here. To the right is shown the heat gain from the reservoir. So whenever we compress, we have the heating up of the reservoir, right? And whenever we expand, we have the cooling. That's why there's also an analysis on the heat The negative sign and positive signs indicates if it's going in or going out, and then it is up to the up to the engineers to decide which way is in, which way is out. As long as you're aware is negative in or negative out, then it is fine. Some equations here, this can be very useful for those who are into like power generation. So, and also compression. So here in this case, this work, it is valid for both generation of, how to say, the energy required to compress and also the energy that we can get from expansion, right? And here we're talking about, in these two red rectangles, the work for closed system, so minus PDV, and then we can develop this to get this equation. We have the open system, that is VDP, and then if we develop it, we get this equation. The difference between the open system, the energy, so if you divide everything by time, so let's say you have a volume flow rate, so V dot instead of V, then you have the power in watts. If you don't divide by time, meaning that if you take the whole volume, that means you have the energy in joule. So these two equations are valid for both energy and power. The difference between the open system and the closed system, the energy, it is just the delta PV over here. So I can rewrite this equals to delta, in parentheses PV. So P2, V2 minus P1, V1. I had in mind to derive this together with you, but I think maybe it's too deep into the theory. So I will maybe just show you quickly how it is done without writing it in detail. This one, the one that I showed you here, it is for non-isothermal, meaning that you have temperature increase when you compress and you have temperature drop when you expand. This equation 2.2, compressed energy storage, isothermal. This means that we have N over here equals to 1. So, I mean, you know, for ideal gas, PV equals to mRT. If this is a constant, so if the temperature doesn't change, oh, I think my pen is dying. So here, let's see, equals to constant. That means the power index that is to the V over here is equal to 1, right? Because PV equals to mRT and we're in the isothermal condition. So here N is equal to 1. With this, we can derive this minus PDV and also the VDP for work in the closed system and also work in an open system. And they come down to the same equation. So P1 V1 times log of the P2 divided by P1. Very often in open system, we talk about the inlets and the outlets. And then in a closed system where we have a piston or a balloon, we talk about state 1, initial state, and the final states. The difference between open system and closed system is that open system, you have a flow through your compressor, your turbine. And then in a closed system, you have basically a fixed amount of a reservoir. I mean, not a fixed amount, but you have a closed reservoir where you don't have mass transfer in and out of the system. And here, work of the closed system is the same as the open system. And then also here, P is pressure, V is the volume, right? So, and N is the heat capacity ratio. And this is Cp over Cv. Sometimes we write K in some nomenclature, so it depends. Here I put N as the abbreviation that I use here. And very important that you don't confuse this with the mole N, right? Sometimes when we say PV equals to nRT, also in mole, so equals to N big RT, this is a different N. This N is the number of moles, right? So here this ratio is very different from here. Okay, I think it's okay like that. From this end over there. Those are two different ends. So I will just erase this equation so we don't get confused. I prefer to work with mass when we're in engineering. So mass times R, and this R, what is this small r? R is the big R, 8.314 divided by the molecular weights of air, right? If we're compressing air. So let's see if I can use a pen. I will use my finger here, pen. So here, this one, this is big R, gas constant, divided by the molar mass. And then the molar mass of air, you know, it's 0.029 because of 21% of oxygen and 78% or 79% of nitrogen. I was thinking of deriving this live here, but I don't think we have to. I mean, if I do this live, you may think to memorize it, but I think it's not worth it to. Okay, let's see. We lost the. Okay, duplicate. Let me duplicate again. Is it still on? Yeah, it should be on. Let's see. How come I don't see it? Okay, here we go. So this is actually the way to derive the work that we saw earlier for an open system. I will make this available, I think, so that you will see it also on Canvas as the course material. Basically, what we are doing here is that we replace the V by this. We know PV to the power of n is a constant, so we can rewrite V in this format. And then if you integrate it, you get this n over n minus 1 delta in parentheses a PV. And then if you sort of redevelop or rewrite it so that we get rid of one of the unknowns, because here you see you have 4 unknowns, P outs, V outs, P in, V in, by rearranging it with this, because we know PV to the power of n is a constant. So basically we can get rid of one unknown, right? So P1 V1 to the power of n equals to P2 V2 to the power of n. That's how we get rid of one unknown. And then at the end, we get to this equation. Maybe it's not so important to know by heart, because you can always refer back to the slides how we derive it. But then it's important to try out a few numbers. So let's say we start at ambient pressure. So 1 bar, that is 10 to the power of 5 Pascal times volume. So, or a flow rate if you're talking about power. So let's say I have 1 kilogram per second of a flow rate here. This would be V dot, 1 kilo per second. And then the P out, if we say we're working in the Hontorf condition, so let's say 72 bars, that will be the P out. Then you can calculate the power that is required to compress it. And then this N, very often this N, we can assume it's an isentropic efficiency to get a theoretical value, or you can take the real N, which is the polytropic term that we can use, the ratio. So here, very often for air, we take 1.4. And then when we say it's polytropic, so considering some of the losses, then we can take 1.3. But when we talk about isentropic case, then for diatomic molecules, so for O2, when there are 2 molecules, so O2 or N2, it is 1.4, this N. So the ratio of Cp over Cv is 1.4, roughly, Cp over Cv. When we talk about monoatomic, so helium, very stable gas, right? That N will be 1.6, 1.666, etc. Or was it 5 over 3? I think it's 5 over 3. No, sorry. Yeah, exactly, 5 over 3. And this one, it's like 7 over 5. This will be the Cp over Cv for monoatomic gas. Let's continue. And then here, we don't need to, I don't want to do this by hand. So I will just done. For the closed system, earlier it was open system, and this one is closed system. So the same, we are using this PV to the power of n is equal to a constant. So minus PdV, that is a definition, right? So this one is always true. This one is always true. And we just replace the P inside by constant over V to the power of n. By integrating it, we get to this term here, or this writing. The only difference between closed and open system is that in the closed system, the numerator is 1. And in the open system, you have a numerator of n, meaning that it takes more energy to compress air or any gas in an open system. This is because you have a flow. In an open system, you have to push the flow from inlet to the outlet. So that's why it requires more energy. And in a closed system, you have a confined space, confined container. That's why you have a slightly smaller compression energy or expansion energy you can get out. And then since this is always true, so the ones I'm putting double brackets, it's always true. This one is always true too, right? So by knowing this P2 V2 to the power of n equals to P1 V1 to the power of n, we can get rid of one unknown. And that's how we get to this final equation for a closed system. So the same, if you know, let's say, initial pressure, initial volume, and you know the end pressure. So basically, if by knowing 3 of all the unknowns, you can calculate the work that is required. So you can maybe compare the work required for closed system to that of open system for the contour case on your own later on. And then thermal case. So earlier we were in the non-isothermal, meaning that the temperature would increase if you compress and temperature would drop if you expand. And now I'm showing you the case for isothermal conditions over here. And earlier, I just show you why n is equal to 1. This is because PV to the power of n is always equal to a constant. And you know that PV for ideal gas law equals to mRT is a constant. That means PV n is equal to PV. This means n is equal to 1, right? So in this case, it's very simple. We take the definition of closed system minus PdV for a closed system. And also, for me, I would prefer to write work for a closed system as minus PdV, and then work for open system as a plus VdP. I know there are some other, let's say, researchers who prefer the other way around, but I prefer to stick with this, and it will be much easier for you to follow the same, let's say, standard as I'm using here. And then we know that we can replace the P by constant over V. There's no more, n here is equal to 1, right? So that means we get a log. If we integrate it, we get a log. So this is the results. P1 V1 times log V1 over V2. We can rewrite it because we know P1 V1 is equal to P2 V2. Here, a pen. This one. So then by knowing the pressure ratio, so even if you don't know the volume of the V2, but only by knowing to which pressure you want to compress it to, you can calculate the work required. The same goes for the open system. So here, this is the work or energy or power for open system, depending on if you divide by time or not. You get the same, exactly the same equation. And then for an open system, I normally say inlet and outlet, right? And then here, I have the ratio of the pressure, the compression ratio, but it's also possible to replace this P out divided by P in by V in divided by V out. Yeah, so that's it for now. Any questions so far? Maybe you'll need to take a few minutes at home to go through this quietly, so alone, so then you can see what are the mathematical steps. I would say the most difficult part is to list down the known equations, the ones that are known by definition. So again, the equations that are known here, I'm showing you here, is that PV to the power of n is a constant, always true. We know PV is equal to MRT. So maybe I need to rewrite this equals to MRT. For me, the small r is basically the big R over the molecular weight. And then also the one I put in red, this is a direct consequence of these two first equations. So here, basically, by knowing two unknowns, you can know, by knowing three of the unknowns, you can get to know the fourth parameter. So if you know the temperature ratio and you know one pressure, you can calculate the other pressure. Or if you know the volume flow rates at the inlets and at the outlets, and by knowing one of this unknown, then you can get the other one, right? So this is a very powerful equation over here, or outcome, by combining PV to the power of n equals to constant and PV equals to nRT. But this is, of course, valid only for ideal gas. If you're having non-ideal gas, you may have a correction factor in the PV equation over there, right? So this, the one in red, this is for ideal gas. Maybe I need to write this. This is ideal gas, IG, because we are using the ideal gas equation. And then if we want to have some more illustration, a picture that's more representative to place it in this PV diagram. So y-axis is pressure, x-axis that's volume. We know from definition, so this is definition, closed system, it's minus PdV, and we know the open system, it is integration of VdP, right? EP. And then, so we know that this, the area in gray, this is the closed system. And then I'm going to draw this, and the area in red here, this is the open system work, or energy. In this case, it's energy. And then if you subtract them, what you get is this delta P1 V1 minus delta P2 V2. That's the difference in terms of the work that we explained just earlier here. Work open system minus work closed system is P2 V2 minus P1 V1. And you see that directly from this graph over here. So here they put final and initial, but initial is 1, final is 2. And then initial is 1 and final is 2. Very good. And then the same can be seen also here for the expansion case. I mean, at the end, the difference, yeah, I mean, you see from the graph, right? So P1 V1, it is the area. I don't know if I can change the color. P1 V1 is this box. And then P2 V2. Let's see if I can use another color. And then P2 V2, it's this box. If you minus, I mean, if you subtract these two boxes, it's the same as if you subtract the red area to that of the gray area, right? It's the same. And then what is interesting to see is that in the compression state over here, compression, the isothermal case would require the least amount of energy. If you're compressing it isothermally, the amount of energy needed is the least. And then in the adiabatic system, where you generate heat as a waste heat, that's a loss, right? You need to provide more energy for your compression, because part of this work or energy is lost as heat. And the polytropic one, that's the case in between. So I would say that's closer to the real case in this case. And then the same for expansion. If you have isothermal expansion, it gives you the highest amount of energy or power if you divide the energy by time. And then the adiabatic one, since you're taking the heat away, so you lose some pressure. So the cooler you will have, right, the lower the pressure or the lower the volume. And then the hotter it is, the higher the volume or higher the pressure. So when you expand it, if it's taking some heat from your system, you're going to lose your energy. So that's why the adiabatic one has the smallest work or energy that can be extracted. Let's continue. And I think maybe this exercise we can work together. So this is a direct exercise of calculating work that is required to compress 1 ton of air from 1 bar at 25 degrees Celsius to 72 bar. So this is a direct application of the equation that we have seen. Consider isentropic process. So what is isentropic? Isentropic means adiabatic and reversible. Oh, sorry. I think earlier I was confused. So here, sorry. Yes, in this case, adiabatic means that we are not losing heat. Sorry. So my bad. I was referring to diabatic, but here this is the adiabatic. We're not losing any heat, and then the work that is inside the system is the highest over here. In the isothermal case, I'm sort of like extracting, cooling down. I'm getting all the energy away. So my bad on the graph over there. So here, adiabatic and reversible, that's isentropic process with the ratio of Cp to Cv as 1.4. We assume it's ideal gas. Yeah, sorry.
So you mean adiabatic requires the most amount of energy to compress?
So in this specific figure, yes, we see that in the adiabatic case, because the whole storage heats up, it's taking more energy to compress hot air as to compress cold air. So if you cool it down to isothermal, the work that is required to compress it would be less. So I was thinking the other way around, that we like generate heat and then we remove that heat. But here, adiabatic means that we contain the heat. We use this. I mean, the heat that is generated is actually heating up your air, let's say, or your fluid. So that's why it takes more energy to compress hot air than as compared to cold air. That's also why you have interstage coolers for compressors, where you cool down at intermediate stage between the stages. And then the other way around is valid for the expansion. In the adiabatic case, you are actually extracting heat because we don't have any heat coming from the outside. So the gas inside, it is taking the heat from itself. So then it becomes cooler, or let's say it becomes lower pressure, it becomes less volume. So then the amount of energy you can get out, it is less in the expansion. Another question, or yeah?
Yeah, I was wondering, like, I mean, for me, but then assuming we would do like compression and then expansion afterwards, and after compression with adiabatic, I would have way higher temperature.
Exactly.
And then during the expansion, I would go from very high temperature down, right? So
but we lose. Let's say I store my okay, let's say I have my storage, and then you're saying that if we keep it maintained at that high temperature, and then we expand it, but during the expansion we don't maintain that temperature, that temperature drops. Isothermal means that we are always working at the same temperature. So if we start at, let's say, 700 degrees, and then in an adiabatic system, the heat inside the system is being taken by the expansion, let's say, phase. And then that will mean some of this energy is lost.
Yeah. But okay, and then for the right graph, for the expansion, they both start at the same temperature, or like all the three.
Right. So here, this is only schematic purpose. So we're saying that comparing them all at 700 degrees, or all at the room temperature. So then we get more energy back if it's isothermal, as compared to the case where we lose the heat, because it's adiabatic, so it's confined. And then also it's very important not to mix this with the storage period. So we can say it's an adiabatic storage period where we don't have heat loss, because if you're having compressed air at 700 degrees, the system would very likely to lose heat. And then very often we also use the term adiabatic compressed air energy storage during this storage period where we have good insulation, and that's slightly different from here. This is the adiabatic compression and not the adiabatic storage, right?
And then, but the conclusion from these graphs would be that isothermal would be the process we would prefer.
Sure. Yes, it is. It is. But then it is very difficult to get this isothermal, because either we need to go very slowly, so that let's say we have some temperature increase, that's temperature we wait until it goes back into, same temperature level, or we have to extract some of the heat. And then the heat we extract, if we have a use of this heat, then it's good. But then if to maintain this and we extract all the heat, we dump the heat away, maybe then that is not so wise, I would say. So it all depends on what we use with the heat that is generated. Let's have a quick exercise here. So 1 ton of air from 1 bar at 25 degrees Celsius to 72 bar. Consider isentropic. So here, adiabatic reversible. Assume ideal gas. The molar mass of the air is 0.029 kilogram per mole. So if we want to put it directly into the equations that we had earlier, so W, this one is open system, right? Yeah, we can say we are working with the open system. Then the equation was n over n minus 1. P in, or P1 V1, which is inlet also, P in V in, divided by P out over P in, n minus 1 over n minus 1. Here we have the pressure ratio, because we know it is 1 bar to 72 bar, but we don't have the V1. How do we get the V1? We use the ideal gas equation. PV, so P1 V1 equals to, or P inlet, V inlet equals to MRT. And this is, we know the big R is 8.314. And then the M, or the molecular weight, 0.029. The mass, we also have the mass. Actually, I can just write it directly, 1,000. So in engineering, it's kilogram, it's joule, it is Kelvin, right, that we use. And it is second that we use. Did I lose anything that, okay, here. So, and then we use Kelvin plus 25. And then we know the pressure. Pressure, it is 1 bar, that's 10 to the power of 5 Pascal. And we use Pascal in engineering. So this would give us the volume of 854.7 cubic meter. And then we put this into there. We know P1, it's 10 to the power of 5. we know the ratio is 72, right? The whole thing here is 72 because we go from 1 bar to 72 bar. We know n, it is 1.4. So then we can calculate this work of the open system. That would be, I mean, if you do all the calculation, okay, I can write everything down. So we are sure we have everything. 854.7 divided by 1.4 minus 1 times, we say the ratio is 72. And then 1.4 minus 1 over 1.4, everything minus 1, right? And this would give you roughly 7.16 10 to the power of 8 joule. This is 8. And then also in engineering, very likely we will put everything in kilowatt hour, megawatt hour, gigawatt hour. So to convert joule to watt hour, we divide by 3,600. And then this would give us 1.99 10 to the power of 5 watt hour, or roughly 200 kilowatt hour, right? This will be the results. And then if we know that we want to do this within, let's say, 1 hour, we divide this by 1 hour, we get the power. If we know that we have a requirement of doing this in half an hour, then we just divide this by 0.5 to get the power. Because this is the energy, but it doesn't show us the power, the time frame. Question so far? Or is it all good? Yeah.
Can you explain again why you consider an open system?
So it should be given in the exercise, but so here we assume open system. Assume open system. But then of course you can also do the same calculation for a closed system and check the difference. But the difference between open system and a closed system would be a factor of 1.4 from what we saw earlier. That's the so the closed system would require this much divided by 1.4 energy. But you're right, that's the instruction doesn't say close or open. So then either you do both or you choose one to do that. And then let's continue. What is the temperature of this compressed air? And what is the volume? So earlier we know the energy, right? So we can now calculate the temperature of the compressed air. And here we can go back to use this, this equation over here. Of course, you can use the ideal gas equation, number 2 there. But then in this example, yeah, I mean, they would give you the same results. So either this or that would give you the temperature. But maybe we can just use both. Let's do both. So T1 over T2 equals to the pressure ratio, right? So this is what we had earlier. It doesn't, I think the power is dead. Let's see. So I will use a pen, divide by N. And then this would give you the T2. So, I mean, just put T1 to the other side, right? So here you get this 273.15 plus 25 times this pressure ratio, 72. And then you multiply everything by this, I mean, to the power of 1.4 minus 1 over 1.4. So you get 1012 Kelvin. If you prefer to use the ideal gas law, so ideal gas law directly, PV equals to MRT. Nah, it's okay. I think that the first one is good enough. So I think it's the it's very straightforward here. And then what is the volume? Let us calculate directly the volume. So for the so this one is for the temperature, the other one is for the volume. So for the volume, we just put pressure to the other side. we know it's 1,000 kilogram. We know the small r, I think it's 287, right? Or we can recalculate it if you want. So small r, it is this 8.314 divided by 0.029. And then times the temperature 1012. And then we divide everything by the pressure, which is, so it is P2 we want to calculate, P2. So 72 times 10 to the power of 5. And this would give us a volume of 40.3 cubic meter. And of course, so this is one way of doing that, or we can reuse this magic equation that is shown in this red box, right? Because here we know, let's say the temperature, or I mean, we do have either the temperature ratio or the pressure ratio, and we know the inlet's volume. So then we can also use this equation. So I'm giving an alternative way of solving this. Pressure ratio, and then here is the volume ratio. So then we can get the V2. So what is V1? V1, we know that we have 1,000 kilogram of air, right? So 1 kilogram of air, it is 1 cubic meter. Sorry, sorry. We have to calculate that from the P1 V1 equals to MRT to get the volume 1 of the air, right? That is equivalent to this 1,000 kilograms, so 1 ton of air at 1 bar 25. So you need to use this to calculate the V1. And then once you have the V1, then you can get to this equation V2. And it should give you the same 40.3. So sometimes this equation is faster, sometimes it's slower. So it depends. For the first case, this is very fast. But if you want to calculate the V2 from here, it may take more time. So it's up to you to decide what is best. You have to decide, but they will give you the same results. I think we can have a short break. Let me just check if there are many more slides or if we should. We do have some systems here. We may not go that deep into the system analysis. I will continue just slightly a little bit. So I cover this part before we go to the break. So earlier we talked about compressed air storage, but it can very well be liquefied air storage. How do we get to the liquid state? I'm going to show that to you. Okay, so here is a timeline. So the concept was from the 70s. We had a first few patents over there, and then the first few liquid air energy storage as an energy storage system, they came about only 2 decades or 1.5 decades ago. I'm showing you the direct ranking cycle when we want to get the energy out, right? So from liquid air, we evaporate it, we have compressed. Okay, in this specific case, this is liquid air in Kelvin, so very cold. We will need to heat it up, and then we compress it in our expansion, let's say turbine. You can have a recuperator where you recuperate some of the heat that is provided into your system. We'll not go that deep into it. And then how do we make liquid air? So here I'm showing you some processes. There are different ones: Lin, Cloud, Kapitsa, Heyland, Collins. Basically, we compress our air. So we get high pressure and high temperature. We cool down. So it remains at high pressure, but we cool it down here. So this vertical one is compression, and then this this drop in temperature here, a curve that is cooling down. So here we compress, we cool down, we compress, we cool down. So now it's at very high pressure. And then if we expand it, since we know that upon expansion, it is well insulated, it's going to take away all the heat. So then it takes the heat from your compressed air, then it creates some liquid air here, and then some, upon expansion, you have a gas also. So that's how we create liquid air, through expansion of highly compressed air. The same principle goes to the other systems, but then here we can have this expansion already mixed, I would say, or at a higher temperature. So they're like different processes, depending on how we want to set up our system. So if you're interested, you can come here to this different temperature TS diagram to take a look. And with this, I think we can have a short break. Let's come back at 15 past. Is that okay? So we'll come back at 15 past. Thank you. And I will pause the recording. And we will continue with the, so I will just spend maybe one more minute to show you another schematic diagram of high temperature thermal energy storage integrated liquid air energy storage system. Let's see if I can go next. Here we go. So here, to understand how this works, first you need to see the arrow, like which direction it goes. So here we see on the right hand side, you go from high pressure to low pressure, right? Because the shape of this is large here and small there. So here you have an expansion. So to the right here, you have 3 stages of expansion. This is when you discharge the liquid air. And then to the left, this is the charging part, or charging equipments. So here you have going from ambience, let's say, going into a compressor. So it goes in low pressure, it goes, so high volume goes to smaller volume. So low pressure to high pressure. So you're charging up, or you're compressing the air, and then you would send this compressed air into, let's say, a cold box or heat exchanger there to cool down. And then after, when you expand it, so here you see again, it goes into an expansion valve, sort of. So going from high pressure to low pressure, so small volume to larger volume. And then here you have both liquid and gas, or liquid and vapor state of your air. So this is a separator where the let's say the gas or the air goes back here, over here, and then the liquid air, it goes to the storage. And then in this specific case, so this case, I think they call this, I do have the reference. No, I don't have the reference. Let me go back here. There are some additional components. Normally, the process I explained, that should be enough, but then you do have some additional process over there to recuperate or recover some of the thermal energy there. So if you're interested, you can take a deeper look over there. And here you do have a Kalina turbine. You do have a hot water storage, or let's say thermal energy storage units over there to recover and to improve the, let's say, efficiency of the whole cycle over here. But we're not going to go that deep. I give you all these TS diagrams. So you can see to the left, this is for charging. You go from ambience A1, you compress it, you cool it, you compress it, you cool it, you compress it, you cool it. And then at point 10, we expand it. This is the CRT over here. We expand it, and then we get to the point where you have some liquid and some gas. The gas you send back to the compressor, and the liquid 12 you store it. And the storage is here. This LAT. This is a liquid air tank. The expansion then is the other way around. We go from, let's say, over here, liquid air, we heat it up, or we use the recuperated heat to heat it up, and then we expand it. So then we get all this expansion energy. And then here, this heat will be used to heat up this stage. All right, so that's about it for liquid air. And then, yes, and then additional process, that's so like 46 to 51, it is this over here, here, the Kalina process. So you can take a closer look if you're interested. Then let's move on to some exergy aspect. This is very important concept. Most of you may have already seen this a few times, but here I just want to make sure that everybody's on the same page. So an analogy of energy is that, let's say you have two students, one is studying for 20 credits, one is studying for 40 credits. If the student studying for 20 credits uses only half the time as the students A, then they have the same energy efficiency, right? So the total energy or the total credits, they are different, but then the speed or the efficiency is the same. But then the Exergy, what is Exergy? It is more on the quality. So even though they all have, let's say, 20 credits for every half a year, but student A gets A++. Sorry, the student A is from, let's say, MIT or Harvard, Cambridge. So he or she should be extremely good. And then student B, never gone to school, just came because he or she is very bright. And then so the expected outcome will be slightly lower than the one who has gone through all those years of education. But at the results actually show that student B gets a C and student A gets a B. So the Exergy efficiency of student B is much higher. So the quality, so the potential for him or her to get a C actually allows him or her to get a C. So this is extremely good. So matching the expectation. While for student A, bright school, but then he or she, even though the absolute term is higher here, B, but then still from the Exergy efficiency perspective, it's much lower. So this is an sort of an analogy. It's not exactly like this, but you can understand it this way. So one is the total amount of energy, I'd say, and the other one is more the capability of providing work. And in terms of, let's say, thermal engineering, it is actually the temperature level. The higher the temperature level, the higher, the higher the temperature level you can get out, the higher the Exergy efficiency. And then you know that electricity has the highest Exergy efficiency because electricity can be converted to any source of work, mechanical, thermal, etc. Yeah, let's continue. So there are some fundamental equations for you to, not to memorize, but for you to know where to find. So Exergy is very similar to enthalpy, right? Enthalpy, you know that it has to be benchmarked against a reference value. So this is why in the first equation here, I have my absolute Exergy that is actually benchmarked to my reference case, 0. So U is internal energy, V is the volume, S entropy, big V is the velocity, right? So mv squared over 2, you know that equation. And then from the hydro lecture, you also know that mg zeta, that is also the that's an energy potential. It's due to the height. And then when we talk about Exergy, we very often think of the amount of Exergy or like work that can be extracted when we go from state 1 to state 2. So the delta Exergy, this is actually the Exergy we refer to. It is mass times the change in your internal energy from state 1 to state 2. So basically, let's see if I can use, I changed the battery, so now my pen should work much better. Exergy 1, or sorry, Exergy 2 minus Exergy 1. Minus Exergy 1. This is the delta Exergy, right? So basically, if you replace all this by U1, V1, S1, big V1, big Zeta1, and then you put the whole thing here, and then you replace U, V, S, big V, and Zeta by this state 2, then you get to this equation. This is for closed system. For open system, we don't use internal energy. We don't use U anymore. And also, like, how do you calculate U? U, it's CV, right? MCV delta T, that is for U. And then what is H? H, it's CP, right? That's how we differentiate this U from H. And then also, when we have an open system, we no longer have the this PDV, right? So that's also another difference. But this one gives you the exergy of a, change of a system for an open system. So mass times the enthalpy change minus the exergy that is destroyed. So this part is the exergy destroyed. Exergy destroyed. And then also the same here. This one, it is the exergy destroyed. So very often in some exercises we see that, oh, how much exergy did we destroy if we use electricity to heat up water, and then we can sort of calculate it this way. Yeah, let's continue. And then another way of understanding it is like this one is your enthalpy change, right? Like over here. That's another way of understanding it. Any questions so far? Yeah.
Just explain again. What's the variables set?
Right. So all the variables. So each of this is a variable. So U is the internal energy, or anything with an index. Those are the variables. So T0 means it's the ambient temperature. So a cup of hot water. Let's say a cup of water at 20 degrees. Now here, maybe it's not having so much of a potential, but this cup of water, if it is in a real cold climate, let's say minus 40 degrees, it has a lot of potential, right? So that's why we always refer or benchmark the destroyed exergy to the ambient condition. That's why there's a T0. If the ambient condition is extremely warm, it will give you a different result. If the ambient condition is very cold, it would give you a different result here. And then all this big V1, big V2, those are the velocity. They are variables too. So if you start a car from like stationary to 100 kilometers an hour, here you have a change, right, in your energy content there, or let's say exergy. The same here, zeta. So if you have a pumped hydro, if you let it go from high upper reservoir to a lower reservoir, and then there's also an exergy potential there. Yeah. Yes, please.
And the other V is then volume.
So this one is exactly. So here we are actually, it's specific volume because I have my mass in the front. So basically it's the volume divided by mass. That's why I have the squiggly V. And everything here is specific, so specific internal energy, because I have my mass in the front, a specific entropy, and then the big V, it is direct velocity, because we need to have mv squared, right, divided by 2. And then also the let's say the height potential, this is the mg delta z. So it's in meter for the zeta here. So those are some fundamental equations for closed system and for open system. So closed system meaning that there's nothing flowing in or out. And then the open system means there's a flow. And then the exergy that is destroyed. So earlier, like this term, I put a big red box around, right? This is the exergy that's destroyed. Let's take a closer look at that. So for non-compressible solid and fluid, the exergy that is destroyed is basically the mass times the, let's say, the average specific heat capacity C, times the T ambient times log state 2 to state 1. So this one is for non-compressible solid and fluid. And then if you're having, let's say, a gas that is compressible, right? And if we use ideal gas, I mean, we always like to use ideal gas because real gas, you need to have a lot of correction factors. It's not so nice for the equations here. But if we take ideal gas in a closed system, so the first one is for closed system. This is the equation we get. So mass times the temperature with the integration of entropy, you get to this term here. It's slightly complicated, but then I think I will have time to show you how we get this. So basically it's a ratio of the temperature, state 2, state 1, and a ratio of volume, state 2, state 1. And then for an open system, everything is unchanged, but it is the sign here, right? It's minus, and then it's the ratio of the pressure. And this one is, yeah, I mean, for an open system, it's the, I mean, very often to remember it, we have to know that it's the H. And then, so H, it's linked to pressure. And very often when we talk about the closed system, it's internal energy. And then that is very often linked to the volume change. But everything here I circled in red, these three equations, they are important equations to calculate the destroyed exergy. Whenever you have a temperature change, whenever you have a volume change, whenever you have a pressure change, they can be calculated this way. And then my plan was actually to go through the derivation step by step, but I don't know if we'll have time to do that. I think it should be fine. Let's do it one together. Have I done this with you before or not yet? No, not yet, right? So exercise, derive the destroyed exergy. So this is for a non-compressible or closed system, let's say closed system. Here, let's see. No, do we have it? Oh, sorry. This one is for a closed system. So we go for, okay, non-compressible. So we go for the first one. Solid and fluid, non-compressible, solid and fluid. And it's the same for open or closed. When it's non-compressible, it doesn't matter so much. So exergy, destroyed. This one, by definition, is mass times T0 or T ambient times the integration of entropy from state 1 to state 2. This is definition. So nothing to I mean, just have to remember this definition. And then another definition is that what is ds? ds is delta Q over temperature, right? Heat, the change of heat over temperature, this is your entropy. That's the definition of entropy. So nothing to worry about. We just write them down. So if we replace ds by squiggly dq over temperature, so the exergy destroyed will be mass times the ambient temperature times this. Okay, you also know that what is Q? Q is C dP, right? So C times dt. I mean, this is definition. Because very often we say MCP delta T. This is the energy. This is the Q, the heat. So if I replace everything here, oh, I need to remember to have the integration over here, state 1 to state 2. Of course, the C specific heat capacity changes as a function of temperature, but in this case, let's say we take just the average, or we assume it's a constant. So C average times the integration of dt over t. You know the integration of dt over t, it's log t. So you get to m T ambient C average log T2 over T1. And that is the equation that we got, right? So this one is the destroyed exergy for non-compressible solid or fluid. So very often we say liquid fluid is non-compressible. So here, solid or liquid. If it's gas, it means there's this other equation, gas equation we have to, I mean, it's compressible, so we have to consider that. Everything good so far? Yeah. And then the next one is slightly more complicated because I also want to derive the destroyed exergy for compressible, both closed system and open system. So we just did this one. Now I want to do the derivation for this number 2 and number 3. So maybe I just say number 1, number 2, number 3. So this one is number 1. Let's do it for number 2. Equation number 2, compressed closed system. Do you need to have more time or is it okay? Yeah, it's fine. It's fine. So let's do it for number 2. Here again, let's list down everything we know. We know by definition, heat and work, right? Conservation of energy. So this one is a closed system. Closed system. This one is equal to the change of internal energy. That's just definition. And then also definition, what is Q? Q, it's earlier we say T times ds, right? So the entropy is squiggly Q divided by the temperature. So I'm just rewriting it this way. And then what is work? This is equal, so it should be straight. It is, so closed system. And this is the tricky part. You should not mix up closed system with open system. Closed system is minus P dV, right? We have been doing that in the first hour. Open system, VdP, but closed system minus P dV. So those are definition. So if we put Q, so here, and if we put the work inside, so let's say the star equation will become TdS equals to d. Okay, I also put the work on the other side because I don't want to have the minus sign, plus PdV, right? This is a direct recombination of the definitions. Straightforward. And then if we divide everywhere by T, so ds equals to du over T, right? P over T dV. I'm just putting T on the other side. And then this with the ideal gas. So here comes the ideal gas. The internal energy, it's so U, what is U? What is du? Du, it's mCv delta T, right? So here we know the internal energy is mCv delta T. Oh, and here I put everything in big S. That means it is no longer specific. Here I have the entropy and not entropy per mass. Here I have the internal energy, not the internal energy by mass, right? So I'm having everything written in big with big letters plus, and then what is P over V? We know that PV equals to mRT. So P over V, this is a mistake, T, right? I divide everything by T. So P over T, it is mR over V, and then dV. The reason for rewriting it is this because we want to integrate. So this is much easier to integrate because we get log. So if we integrate everything, or let's say if we want to remove the mass, so if we want to write in small s, so d big S over mass, or the d small s, that means we have CV over T. Okay, this is also small v. This is specific heat capacity times dt plus R times dV over V, right? And then if we integrate this, so small s, so specific, let's see, s, small s, this is equal to just the integration of the above, d small s. And then this is going to give you, what is it? T ambient. Oh, here, no. Okay, let me just say, rewrite CV log T2 over T1 plus R log V2 over V1, right? And then what is the Exergy destroyed? So the Exergy destroyed, again, this one is M times T ambient times this integration of small ds. So we just replace everything here, there, to the integration of ds. So this would give, I don't have enough space, but you know, right? So if maybe I can just use the space that is down there, equals to mass T ambient times, and then just rewrite everything. CV log T2 over T1 plus R log V2 over V1, right? And this is the Exergy destroyed for a compressible gas in a closed system. Yes, please.
Only for ideal gas.
Only for ideal gas. For non-ideal gas, you will have a correction factor, or let's say a polynomial for the temperature. So this is only valid for ideal gas, starting from this point onwards. So let me change the color. So from this point onward, it is ideal gas. And we can do the same for an open system. So you know that compressible, I mean, for any system, you can have closed system or open system. So closed system, a balloon or piston. And then if you have a turbine or a compressor, that is an open system. Because you take it from one side, you send it out on the other side. So let's do this. Do I need to stay a few more minutes here, or is it okay? Is it fine? Then I can continue with the derivation of the Exergy destroyed for compressible gas in an open system, where earlier we saw that the energy for an open system is much higher, right? So let's go to that part. And here, what is important is to know, or it's important to state the definitions. So we're going to do the same. dq, is it too light? Maybe I can use the red pen instead. Here, I will change the color so you see much better over here. So dq plus dw equals to, okay, this is open system. In an open system, we use enthalpy, right? So this equals to enthalpy. And then you know, by definition, dq equals to tds. This is always true, no matter closed open system. Yeah. And then delta W open system, this is very important not to confuse this with closed system. It is VDP, right? We have seen this in the first hour. So I have listed down all the definitions. This is by heart, nothing to use mathematics for, just memorize this. And then if I replace Q and work in an open system into the star equation, I get, what do I get? I get TDS equals to DH minus VDP. Because I want to calculate DS, that's why I put the rest on the other side. And then if I divide everything by big temperature here, minus V over T dP. I get this. And then if we are having an ideal gas, IG, ideal gas condition, I know that's what is H? dH is mCp delta T, right? mCp delta T over time. Oh, sorry, over temperature minus, and earlier we say what is PV in ideal gas? PV is equal to mRT, right? So here V over T, I have M times R over pressure. This is ideal gas law, dP, because PV equals to mRT. That's why I have this. V over temperature is mR over P. And now it's very easy to integrate. Yes, now you see you have a log and log, right? So the same, let's say Exergy destroyed for open system is equal to, this is definition of the Exergy destroyed, like mass times T0 or T ambient times the change in your entropy. So from entropy, you get to calculate the destroyed Exergy. And then this one is MT ambient. And if you integrate everything here, right, you have a log. And also here, this is a big S. If you want to write it in small s, you just remove the mass. So here, let me just rewrite it. So the small s, it is Cp dt over T plus R dP over P, right? This is specific entropy. So now I'm integrating this one. This would give me, and also I assume my Cp is a constant, just to simplify it. This would give me Cp, the average one. The previous one is a CV, right? And here it's a CP. That's also something important to remember. Open system, it's CP. Closed system, it's CV. And then here it's temperature 2 over temperature 1 minus R. Oh, I think I made a miss. No, it's good. This is R. Log P2 over P1. Right? So here you go. For the derivation of the Exergy destroyed for an open system for compressible gas or compressible fluid. Any questions so far? This is very mathematical. And maybe here I wasn't very clear with a CV. No, I was clear. Okay, here I put CV here. Yeah, exactly. So this is good. And here we've just demonstrated the equation 3, right? It's the same notation as I have here. So this one is 1, this one is 2, and then this one is equation 3. Any questions so far? No? Very good. Let's do an exercise. So I'm having a refrigerant R134A. Now it's slowly being phased out also. We don't want to have this refrigerant anymore. But here in this example, we still have this. It is compressed from 0.14 megapascal at minus 10 degrees Celsius to 0.8 megapascal, giving 50 degrees Celsius after the compression. Because when we have compression, it's endothermic. No, sorry, it's how do you say, exothermic. So it heats up, right? And then outdoor temperature is 20 degrees Celsius. What is the theoretical minimum work? So first, we want to calculate the potential available energy. So the Exergy that we have here, when we have this kind of change from condition 1. So this one is condition 1. This is condition 2. So if we just rewrite the equation of Exergy that we have from this system, this is an open system. We know that it is, so I rewrite the equation that I had before. So it's the, H2 minus H1, right? For an open system, minus the Exergy that is destroyed. So S2 minus S1. So all these are small ones. This I put the mass in the front. S1, S2 here, and then plus V2 square minus V1 square. This is the velocity over 2, plus the potential energy in the height. Of course, here I'm not considering any chemical potential, but if it's a chemical reaction, you need to consider also the chemical potential, etc., kinetic potential, reaction potential, etc. And here, I think we can just assume there's no flow, and then we are at the same level. We're not changing the height of our system. So this would simplify very much to 4 unknowns that we have to read from a table or calculate it. And here I propose we read from a table. So I'm going to show you a table where you have the enthalpy for R134A at different pressure and temperature. So it's here. So this is a property. So all these are documented. You can get those from existing data sheets. So at different pressure and different temperature, you get to know. So why is it 140? Yeah, because here we're at 140 kilopascal, right? So we see 140. So this is condition 1, initial condition. And then we are at minus 10 degrees. So now we see the H. This is our enthalpy value, and this is our specific enthalpy value because it's per kilogram, and specific entropy value because it's also per kilogram. So now we just need to write this down. So H1, we say it's 246.4 kilojoule per kilogram. And then S1, it is, sorry, this one was, yeah, and then S1, 0.9724 kilojoule per kilogram Kelvin, right? It's from this table. This is state 1. And then we do the same for 800 kilopascal, 50 degrees. So I have another table here, 800 kilopascal. So this is state 2. 800 kilopascal, 50 degrees. We have 286.7 and 0.9803 kilojoule per kilogram Kelvin for entropy, specific entropy. So I just replace everything in. So H2, 286.7 kilojoule per kilogram. And then S2, earlier we said it is 0.9803 kilojoule per kilogram Kelvin. And the unit here for specific entropy, it's the same as for your CP, right? CP and CV. And the unit for your H over here is the same as like latent heat. I mean, it's the enthalpy, right? So then you calculate this. Since I don't have the mass, let's say specific exergy, so I put small for this open system, would then be this, I mean, if you do the calculations, so 286.7 minus 246.4 minus the ambient temperature, 293.15, right? Because it's 20 degrees ambient temperature, times 0.9803 minus 0.9724. This would give us kilojoule per kilogram, exactly. And this is 38 kilojoule per kilogram. So here, this is the specific entropy for this system. So entropy here, this corresponds to the theoretical minimum work that is required for this compression. And of course, in reality, you may have losses, etc. So then it will be much higher, but this one is like the smallest one. So this is similar to this Carnot concept, like what will be the theoretical maximum efficiency? That will be the Carnot efficiency, right? And here the Exergy allows you to calculate this theoretical minimum work that is needed or the theoretical maximum work you can get out from an expansion. And then I think before we end today, we still have 6 minutes, so we can go for one more exercise. Any questions so far? It's a direct application, right, of your equations. And what is important here is the concept of Exergy. Very often people don't know what it is. It is basically the quality. So earlier we said that if you get an A++, you have a high quality. If you do a lot of credits, so a lot of energy, but all of them are Fx or E, that means you have lower quality, so lower Exergy here. That's an analogy, similar to work and energy over here. So let's do one for argon gas expansion. So we have an argon that is expanded from 3.5 megapascal. So mega means 10 to the power 6, right? So it's 35 atmosphere, 35 bar over here and 100 degrees. And then we expand it to 500 kilopascal. So that means 5 bar, yes. So 35 bar to 5 bar in an adiabatic expansion valve. And then here, when we say adiabatic expansion valve, it means that, yeah, I mean, we will come back to this one. We'll come back here. For environmental conditions of 100 kilopascal and 25 degrees Celsius, determine the exergy of argon. So this is the inlet. So no matter what the outlet is, you can always calculate the potential, right? So here, question A is the exergy of argon at the inlet. And then B, destroyed exergy. So if you go from this to there, under this condition, there will be a destroyed exergy. And then also the efficiency, the exergy efficiency. So basically the exergy efficiency is exergy minus the destroyed exergy divided by the exergy, right? Potential. So let's do this. Some data also is provided here. So you do have the R constants for argon. Earlier when we say let's see if we have air here. Here, air, it's 287 joule per kilogram Kelvin, right? And then if you do the same for the rest, because this is basically, maybe we should write this into small. This is the small r. So small r is big R divided by the molar mass, and then you can get to the other terms here. This is the CP, and that's the CV. So CP is for open system, it's for the enthalpy. CV is for closed system, it's for the internal energy change, U value calculation. And then you have the, okay, and then here, this is the K value or the N value that I mentioned earlier, like PV, power N equals to constant, right? The N value, it is shown here. And you see that for air, which is diatomic, it is 1.4. For argon, it is 5 divided by 3. It is monoatomic. It's only one molecule. Oh, sorry, one argon over there, atom. Let's do this calculation. So the first question, and I think we can manage in 5 minutes, exergy of argon at the inlets. What is the definition of exergy? So, I mean, if we go back to the slide where I have this, where is it? This one. So this is the real potential, right? So, we are in an open system. So we have to take the one with the H over here for the open system. And then here we can assume that there's no height change. There's no velocity flow change. Then it's just this equation. So M delta H minus T delta S. So let me just write this down. So the exergy at state 1 is equal to, so earlier we say, oh, and then this is, let's use the small one. So there's no need for the mass because I don't think we know the mass over there. So here it is H1 minus the reference case, which is the ambient, we can say, minus T0, S1 minus S0. And then what is delta H? Delta H is Cp delta T. So we have Cp, temperature 1 minus temperature 0 minus the ambient, temperature 0 S, and then here, I think we can develop this directly. So what is this S1 minus S0? You can run this integration, right? So basically it's integration of ds, right? And we did this integration earlier from 0 to 1. And which one is that? Where do we have that? We have that over here. This is the integration of ds, right? So we just replace everything there. So we did this process already once. We don't have to do it again. So this one would be Cp T1 minus T0 minus T0. And then I copy and paste everything here. So Cp average log T1 over T0 minus, and then this is R log P1 over P0, right? Because I go from 0 to state 1. So if we replace everything, so Cp, what is Cp of argon? We do have it in this table. So second line, this line, 0.52. Here, so 0.52, I think we can put all the numbers, 03 times, and then what do we have as temperature? It is 100 degrees Celsius. And then what is the ambient? The ambient T0 is 25 degrees. So then we have 100 degrees Celsius minus 25. Since it's a subtraction, we don't have to put it into Kelvin, right? Because it's just a difference that we need. Minus what is T0? And then here, when we have a multiplication, we have to use Kelvin. 298.15. Or we can simplify to 298. We omit all the decimal points. And then here again, Cp 0.5203. And then the log, what is the temperature 1? Here is 100 degrees Celsius. The other one is 25. And again, when it's a division or multiplication, we have to use the Kelvin. It's only in addition, subtraction. Only subtraction that we need to use the, that we can use Celsius without converting it. And then minus, and then the R, what is the R? It is 0.2081. Of course, you can calculate it through the molar mass or so, but we can just put 2081. And then what is the log of P1 over P2? Earlier we'd say it's 35 bar, right? And the ambient, what is the ambient pressure? It is 1 bar. So 35 over 1. So this would give us the potential, the maximum energy potential, so the exergy of my inlet gas. So if you do this, I think if this is calculated or typed in the calculator correctly, 225 kilojoule per kilogram. So this is the absolute maximum potential of your inlet gas. The second question is the second law. No, sorry. The second question is the exergy that is destroyed. So what is the exergy that is destroyed? We can calculate over here. Exergy. How did I write it earlier? Let me see. Delta exergy, right? Destroyed. So this one would be, we just go to the definition, T0 S, okay, ds from state 1 to state 2. So this question is destroyed during the process. So from state 1 to state 2. And then this one would give, so we can go back to the, where's the equation here? Here, so exergy destroyed is this whole thing, right? And then in this specific case, at least from this exercise, they consider we can consider the temperature as a constant in this specific throttling. So they say if this is a throttling process, the temperature would not change. Constant temperature. So then this would be minus R log P2 over P1, right? This is the equation we have. Where do I have it? Here, right? Minus R log P2 over P1. Okay, let's go back to this one here. So log of 1 is 0, so then we don't have to consider that. We just need to calculate the second part. And what does this give us? It gives us 298 times minus 0.2081 times log, and then we say the end, it is 5 bar, start it's 35 bar. So we just replace everything there. 5 over 35. And this would give us 120.7, so 121 actually, kilojoule over per kilogram. And what will be the efficiency? So question 3 here is determine the second law efficiency. Basically, you subtract this two and you divide by the potential exergy. So here the exergy efficiency. And this will be the last step for this exercise. So it's exergy at the inlets minus the exergy that is destroyed divided by the exergy that is at the inlets. So that would give us okay, 224.7 minus 120.7 divided by 224.7. And this would be 46.3%. So in this process, my exergy efficiency is just 46.3. And of course, you can compare this efficiency to the energy efficiency if you want, just to see the difference between the exergy efficiency to that of the energy efficiency. This is the final slide. Are there any questions regarding exergy or compression, expansion of air or gas? This is very useful if you're in the HVAC industry, so heating, ventilation, air conditioning, because you're going to work with this a lot. If not, then thank you all very much for today and see you next time. All right, goodbye for those who are online.